Hi everyone. I will introduce our work about static posterior inference. This is a joint work with Dr. Hongfei, Tengshun, Yang, Guanyan Li, and Wang. In probabilistic programming, we focus on the normalized posterior distribution, which consists of two components, the unnormalized one and the normalizing constant. The latter is usually difficult. In our work, we aim to formally derive the lower and upper bound on NPD. We notice that if we can obtain the bounds on UPD and NC, then we can get the NPD bound directly. To make the NPD bounds well defined, we require that UPD is non-negative and NC should be positive and finite, which implies that P is integrable. Emphasize that the integrability issue of P is non-trivial, and we will show it in the following. In the continuous setting, we find that P is a special case of NC, because they can be expressed as the expression of likelihood. And the difference is that UPD is restricted to some subset U. Then we assume that bounds on UPD and NC can be derived in the same manner. Under this assumption, we can reduce the programs of NPD bounds to the program of NC bound. In our PPL, we have two additional statements. First is by score. The second is simple. We also define two variables. We extend the classic basic transition system and named its variant weighted. Yes, concretely, it is a multiplicative likelihood weight. Subset N means it is the product of all likelihood weight encountered in the state comments after n steps to assign a distribution to the initial program valuation. If there is no score comments equals score 1, consider the Fitzgerald work example at four variables and two separate variables. Let's focus on the loop in the red box. Given an initial program variation V, it can include a program run of Let4 by choosing the branch twice. The final multiplicative likelihood weight of 3 is computed as 4. Recall the version of normalizing constants in our semantics can be rewritten as integrable of expected starting from some V sub 0. Sorry, in our slides, we have used V sub 0 and V sub init. They are equal. Then according to the fact, we can reduce the problem of NC bound to the problem of among the expected weight. Next, we introduce two kinds of programs we support in our work. The first is named scope-end programs, which run only one segment at the end of the program. The second is called score-recursive programs. Around score segments exist inside the loop bodies, and the values of EW can be greater than 1. We find that there exist continuous distributions, continuous observations, and there are unbounded numbers of samples and scopes due to the fact that the programs are all loopy, which makes deriving difficult. Therefore, the integrability issue of score-recursive programs is essential. We also find that some examples in biology can be transformed into score-recursive programs. Now we put a section. Rough idea is that we can construct a new program U by adding a conditional branch immediately before the termination of D, such that the adding constant of the U is equivalent to the UPD on U of the order program. Before we formally introduce our approach, we present two mathematical functions. The first is the state function which maps from a program state to a real number, which is dynamic. The second is called an expanded weight transformer, which is a higher order function that takes as inputs state function the state, then outputs the expected weight of EWTH after one step of the UTTS transition. We define a special state function called weight function, such that value of this function at the initial state is equivalent to the value of the expected weight starting from v sub 0. And by this, we learn a fixed point approach for score at the end programs. The idea is that we prove that EW is a unit fixed point EWT if the program is almost surely terminating and the value of EW is bounded. And by applying this fixed point theorem, we show that for any h of EWT, it is also an bound of EW. Similarly, for any post-fixed point h, it also can be viewed as a lower bound of score-recursive program. We can apply the fixed point approach because we allow a clear number of score statements inside the bodies. Instead, we propose a new variant of optional stopping theorem. The intuition is that to cancel the effect of the multiplicative output weight, we require the exponential decrease in time and the bounded state of program states. When we ensure the satisfactory of condition A1 and A2, we find that a perfect point H of EWT implies a systematic chaos, then it can also be viewed as a bound of EW. Similarly, any post-fixed point H is a lower bound of EW. When we determine the class of the program, we the bounds of EW by polynomial solving. The solving is that we set H as a polynomial over program variables with P with unknown coefficients A sub i's. Then we check the conditions such as AST, the conditions A1 and A2 by accepting finally, we find the unknown coefficients A sub I by solving optimization programs with polynomial constraints from our approach. The technique of program solving is used in program verification, so users can view the rest work for more details. Once we get up and low of the expected weight, we integrate them, and finally we produce the NPD pounds. This is the whole picture of our approach. We first reduce NPD to weight, and then we develop new approach to compute the bounds of EW, and finally we integrate them. There are two kinds of existing methods about posterior inference. The first is approximate approach, and the second is the exact method. Both of them have their own disadvantages, and the most relevant approach is GABI, which uses type systems and also produce NPD bounds. However, GABI is limited to basic explosion, and it doesn't support score-recursive programs. We show the effectiveness of our approach a large variety of branch. We first address no examples that cannot be addressed by existing tools, and we show that all examples doesn't work with 3 examples typed in 100 seconds. And our derived bounds match the simulation results very well. Secondly, we compare our approach with Gabi on NPD bounds. We show that our approach is up to 15 times faster than Gabi, where we can still obtain tight or at least comparable. Finally, we compare with Gabi on pitch probability estimation. We that Gabi produced a wrong result sample. To conclude, we establish a point theory and a multiplicative OST. We adjust score at any program and programs whose integrability is non-trivial. We also stop continuous distribution or unbounded number of loops. We omit few technical methods to tighten our results. In the future, we'll explore more complicated programs and investigate approach to further tighten our results. OK， 下周先。